virtually for this training and learning online faculty development program on emerging trends in space and computing technologies. The aim of this FDP is to provide an in-depth understanding of the latest developments in space technologies, such as satellite communications, space exploration, rocket science, and computing technologies, including cloud computing, artificial intelligence, machine learning, and quantum computing. We believe this will help the participants to acquire knowledge and skills in space exploration and advanced computing, thus empowering them to improve their teaching. Besides, it will also encourage them to engage in creative research and play a key role in the development of these technologies. Though we are connecting from different locations, technology has brought us together on this platform to explore, learn, and innovate. We are greatly honored to have our chairman, Engineer F. Prince Vino, our Honorable Chief Guest, Dr. S. Joseph Winston from Indira Gandhi Atomic Research Kalpaka, our esteemed speakers from Indian Space Research Organization, Defense Research and Development Organization, University of Glasgow, Scotland, Manipal Institute of Technology and AJ Institute of Engineering and Technology, Manipal, and our beloved participants from all over India join us in this inaugural session. Let's make this program an enriching and interactive experience. Let's begin this journey of knowledge together. Firstly, I would like to invite the FDP coordinator, Professor G.W. Martin, the head of EEE department, to deliver the welcome address.
Respected Chairman, Honorable Principal, distinguished guests, and dear participants, it is with great privilege and honor I extend a warm welcome to you all on this occasion. Behalf of Marthanam College of Engineering and Technology, Macet, this established faculty development program. First and foremost, I welcome our respected chairman, Engineer F. Prince Vino. Your unwavering support and visionary leadership continue to inspire us. We are deeply grateful for your presence today and for your ongoing commitments to the advancement of our institution. On behalf of Macet family, we welcome you, sir, for this Atal online FDP program. Next, I welcome our respected principal, Dr. C. Sudhagar. Your guidance and support have enabled us to reach new heights, and we are privileged to have you with us in this occasion. Welcome you, sir, for this Atal online FDP program. Next, I welcome our esteemed chief guest, Dr. S. Joseph Winston, Scientific Officer and Head, Remote Handling and Irradiation Experiments Division, Fast Reactor Technology Group, Indira Gandhi Center for Atomic Research, Kalpakam. Welcome you, sir, for this inaugural section of Atal online FDP program. Next, I welcome the resource persons, those who accepted our invitation and shared their knowledges in various sessions. Next, I welcome the co-coordinator of this online FDP program, Dr. J.C. Prabha, and the head of various departments in Macet and faculty members of Macet. And last but not least, I welcome all the faculty members, research scholars, and industrialists of various organizations in India and abroad. Once again, I extend my heartfelt welcome to one and all present here. Let us make the most of this opportunity to learn, growth, and collaborate. Thank you.
Thank you, Professor G.W. Martin, for your warm and inspiring welcome address. Next, it's my honor to invite our esteemed chairman, Engineer F. Prince Vino, to share a few words in this faculty development program.
respected principal of Macet, Dr. C. Sudhakar, my beloved teacher and today's chief guest, Dr. S. Joseph Winston, Scientific Officer, Atomic Research Center, Kalpakam, eminent faculty members from various departments, coordinators of this FDP, Dr. Martin and Dr. J.C. Prabha, participants from Macet and various organizations, good evening. It's my great pleasure to welcome all who gathered here for the Atal Online Faculty Development Program, which is entitled as Emerging Trends in Space and Computing Technologies. This is a remarkable gathering of brilliant minds from across the globe, all united by our shared passion for the perspective of engineering and technology. The objective of the FDP is to create a stimulating environment for industrialists, academicians, and researchers. We have an exceptional lineup of speakers here. Each one is a leader in their respective domain. They bring with them a wealth of knowledge, experience, and insights that promise to enrich our understanding and inspire new directions in our work. I want to acknowledge and congratulate the hard work and dedication of the coordinators of this FDP, Dr. G.W. Martin and Dr. P. J.C. Prabha of our Marthana College of Engineering and Technology, who have spent countless hours ensuring that every detail is meticulously planned and executed. To our attendees, thank you for being here. We encourage you actively participate. Together, we can make this FDP program a memorable and impactful experience that not only enhances our knowledge, but also inspires us to drive positive change in our respective areas. Thank you. And let us have a fantastic sessions. Thank you all.
Thank you, sir, for your insightful words and valuable presence and encouragement to motivate us in our journey of learning and innovation. Now, I have the pleasure of inviting our esteemed principal, Dr. C. Sudhakar, to share his thoughts with us on this faculty development program.
Respected Chairman, Engineer F. Prince Vinod, respected Chief Guest, Dr. S. Joseph Winston, my former colleague. I am very happy to see him after a long time. Welcome, sir. The coordinators of this FDP program, Dr. G.W. Martin and Dr. J.C. Prabha, all participants and resource persons, very good evening. I am happy that today we are inaugurating the AICTE Training and Learning Academic sponsored online faculty development program on emerging trends in space and computing technologies. This program is organized by Department of Electronics and Communication Engineering of Marthana College of Engineering and Technology. I take this opportunity to thank our management for providing all required support and resources. I appreciate and thank the organizers, especially the coordinators, Dr. G.W. Martin and Dr. J.C. Prabha, for their efforts in organizing this event in a successful manner. I thank all eminent resource persons for accepting our invitation. I certainly hope they will certainly enlighten the participants with their expertise. It is also important that many resource persons are from ISRO, Indian Space Research Organization. It is an added value to this faculty development program. As we all know, ISRO is undertaking various projects to make India self-reliant in space technology. I certainly hope that ISRO, the Space Research Organization, projects will help India to become a developed nation before 2047. In this context, it is very relevant one to organize and faculty development program in the topic emerging trends in space and computing technology. I also believe that this FDP will help all participants to work towards achieving their target and for their future research. Best wishes to all participants.
Dr. S. Joseph Winston is an accomplished individual in the field of atomic energy. His area of specialization includes robotics and automation for remote handling, robotic control system development, multi-body kinematic and dynamic studies of serial robotic arms, advanced nonlinear controls, model predictive control for robotics, design and analysis of nuclear reactor core components, nuclear reactor fuel film thermos, mechanical modeling and simulation, numerical simulation of fluid dynamics extended to tsunami analysis. He has guided many BTech and MTech students. Presently, he holds the position of Scientific Officer H and Head of Handling and Irradiation Experiments Division, Fast Reactor Technology Group, Indira Gandhi Center for Atomic Research, Kalpaka. I would like to invite our esteemed chief guest to deliver the address.
Good evening. Thank you for giving a very vivid briefing about my profile. Thank you so much. I am so happy and elated to see my beloved friend, Prince, Mr. Prince. I'm very, very happy. And also today it is an occasion for me because both the organization, MACT as well as ISRO, are very close to my heart. Because NACT, though I have visited 7 or 8 years back, I don't know whether Prince will remember that. I think somewhere very early I visited once, long ago. But after a long time, again back to this college through this virtual connect, I'm so happy. And let me thank Mr. Prince for this. And also let me thank the principal for giving me this opportunity, Dr. C. Sudhakar, Dr. G.W. Martin, HOD Tripoli, for the coordinator who has been organizing this program. And let me extend my thank to J.C. Prabha, who is also HOD ECE, who has taken the interest to invite me personally, calling me and said that please be available on this day. And since Vimay being very close to my heart, I was very happy to be here this morning. And when I gone through this FDP program, I was really elated because I have seen an array of brilliant scientists from ISRO giving the addresses on various specialized topics. Even in fact, I was very eager. Let me also take this opportunity to attend some of the lectures if possible. So just I wanted to make only 2 points. I feel there are faculty members, research scholars, and PG students. I just for this FDP program, though I was giving some lectures on FDP program for PSG College of Technology, I used to tell them 2 things. And that is the same thing I just wanted to enumerate here, mainly for the interest of research scholars as well as the PG students, and particularly for the faculty members who can also instill this particular things to the students. So one of the thing is like, see, always I tell a slogan. Whenever I go, I tell a slogan, create, share, and collaborate. Create, share, and collaborate. Creation requires a fundamental understanding of basic science and mathematical abilities. I'll not take much time, only 5 minutes. I'll just give a short this one and then maybe declare this as inaugurated for the beautiful lectures from various eminent scientists. So 2 aspects for this, particularly on this FDP program, because most of these days when I visit my engineering college, I just tell them strengthen on mathematical modeling. And second aspect is the numerical methods. These are the 2 fundamental things, irrespective of discipline. Every student, every research scholar, every PG students, and also the faculty members must instill this particular strength on these students so that they come up very bright, completing the degree. One is the mathematical modeling, right? Starting from the 11th and 12th standard, I have seen this beautiful subject in the mathematics book of 11th standard and 12th standard CBSE syllabus. But very unfortunately, this CBSE mathematical teachers always avoid this particular chapter, and they say that the students need not study, no questions will be asked, and it is neglected. So it is right from the school days, even though the emphasis has been given from through CBSE, but still this has been neglected. Then even though after coming to the engineering also, very rudimentary way students keep learning various uh, methods, particularly failing to really understand how a scientific problem is mathematically defined, which is by through energy minimization, optimization, analytical models to define the scientific problems. Then also suppose somebody enhances the understanding through experimental findings that can be retrofitted into models, mathematical models through empirical models based on the experiment. So basically, one has to emphasize more on the mathematical modeling. So in this FDP program, I also just would like to just sensitize the fact that through the technological development, the student should be emphasized with the strengthening of mathematical modeling on various things that they take up. So formulation from a scientific problem to a mathematical model requires the mathematical skills. Then once that is very often I see students when they come to me for guidance, I always separate the problems like modeling part separate and the numerical method solution phase separate, because everybody confuses with the numerical methods and everything put together, they get confused and come in a state of confusion where they can't progress anything. So once I just separate them apart, okay, spend some time, first few days on doing how to model your problem definition. Once the problem is defined, you just convert it into a mathematical model. So don't look at the numerical methods or any other solution phases. Second, I separate and then tell them very clearly, go into the numerical methods to solve a standard differential ODE, differential equations or PDE, partial differential equations, and particularly linearization of nonlinear problems. These are some of the fundamental ways where one can attempt to solve a tricky mathematical problems which are defined from the first phase. So these two are the aspects I always emphasize on FDP programs, like telling that apart from the technological lectures, these two things mathematically and numerically, the students, the research scholars and the postgraduate students must strengthen themselves so that they can come out colorful by solving very high order problems, very helpful to the robust research organizations like ISRO as well as Department of Atomic Energy. So in this occasion, with this short talk, I just would like to thank all for giving me this opportunity. And also, when I have gone through, I have seen an array of nice lecture points from various senior scientists from ISRO. And I congratulate all and also make and also look forward to a very big success of this FDP program. Thank you so much.
Thank you, sir. Your words were particularly thought-provoking. We greatly appreciate the valuable perspective you shared with us. Thank you once again for gracing us with your presence.
Thank you so much.
Now we have come to the end of the inaugural session. It's my privilege to deliver the vote of thanks for today's inaugural session. Gratitude is when memory is stored in the heart and not in the mind. I would like to begin by thanking the Almighty God for His boundless grace and blessings which made this event possible. Next, I would like to thank our esteemed Chief Guest, Dr. S. Joseph Winston, for graciously accepting our invitation and honoring us with your presence. Thank you for your enlightening words. Your valuable insights have not only inspired us, but also set a clear direction for our upcoming sessions. We truly appreciate your time and efforts in being a part of this event. Next, I would like to extend my gratitude to the Honorable Chairman, Engineer F. Prince Vino, for your continuous support and encouragement in making this event a success. I also thank our principal, Dr. C. Sudhakar, whose vision has greatly contributed in fostering a culture of learning and growth in our institution. A special thanks to all our speakers who have cordially accepted our invitation to enlighten us with your experience despite your tight schedule. For every success, there is a person working behind the scene. In this event, that person is Engineer S. Vijingenius, a well-wisher of Marthandam College of Engineering and Technology, whose dedication in arranging the speakers has made this event a reality. A heartfelt thanks to you. A big thanks to Professor G.W. Martin, our FDP coordinator, for organizing the event and bringing together experts from various fields to enrich our learning experience. Lastly, I would like to thank all our participants and the organizing team for their contributions and enthusiasm. Your involvement has made this event truly special. May the Almighty continue to guide us all with knowledge and wisdom as we continue our journey of learning. Thank you once again. We look forward to a fruitful experience ahead. Thank you. Over to session in charge, Mrs. S. Amuda, Associate Professor, Electronics and Communication Engineering Department, Macet.
Good evening, everyone. It's my great honor and privilege to introduce our esteemed resource person for session of Atal Online Faculty Development Program. We are truly fortunate to have Shri M.S. J. Chandran, former Deputy Director, Reliability and Quality Assurance, ISRO Internal Systems Unit, Trivandrum with us. He acquired B.Tech and M.Tech in Mechanical Engineering from University of Kerala, has more than 30 years of experience in the design and development of mechanical gyroscopes. From the beginning of the career, worked in the design and development of dynamically tuned gyroscope DTG. DTG was first flown in IRS-1A satellite in 1988. Then onwards, DTG has become the workhorse inertial rate sensor in all satellite and launch vehicles missions. He is the principal design engineer for the design and development of high-rate capable miniature DTG for the use in launch vehicle and satellite application. The gyro was qualified and flown in PSLV and number of satellite missions, including Chandrayaan and Mars Orbiter mission. He held many positions like Division Head, Group Director, Deputy Project Director, Associate Program Director, and retired as Deputy Director of Reliability and Quality Assurance Entity of ISRO Inertial Systems Unit, Trivandrum. He had received ISRO Team Leader Award for Design and Development of Miniature DTG in 2008. ISRO Team Leader Award for Design and Development Micro IRU in 2017. Few ISRO team onwards as mentor. Eminent engineer from Institute of Engineers, Chennai. Today, he will be sharing valuable insights on the topic Evolution of Indian Space Program. As we all know, India's greatest achievement is the evolution of space program. What began as a humble dream in 1960s has now placed India among the world's leading spacefaring nations. Over the decades, India made significant advancements. As we look ahead, the Indian space program continues to inspire millions, proving that with determination and vision, even the sky is not the limit. Let us all extend a warm virtual welcome to our distinguished resource person, Shri M.S. Jayachandran of today's online FDP session 1. Now, I request Shri M.S. Jayachandran to engage session 1. Sir, please take over the session.
Good evening, everybody. Am I audible?
Yes, sir. Audible.
Yeah. First, at the outset, I would like to thank the organizers for inviting me to make a lecture on this great program. I would like to thank the management, the chairman of the institution and principal of the Martandam Engineering College. Also, I would like to thank the coordinators, Dr. Martin, as well as Dr. J.C. Prabha, for inviting me uh, for delivering this lecture. Specifically, Dr. J.C. Prabha, she was very coordinating with me. Personally, she was contacting and pursuing me to get all the details, and the efforts taken were tremendous. Thank you. Yeah, thank you, one and all. Uh, I thought before giving this talk, I thought this program, this is the first session, being the first session, it may be apt to give an overview of the Indian space program instead of going to high funda things. This will give where we started, where we made a humble beginning, and where we stand today, and where we are heading to. So that may give a total glimpse of Indian space program and its evolution. Uh, just this Indian space program, we say Dr. Vikram Sarabhai is considered as the father of the Indian space program. So the then Prime Minister, Mrs. Indira Gandhi, invited or she pursued Dr. Sarabhai to take over this assignment to lead this space program. There was no formal space activities happening India. So in late 50s, in 1957, when Russia launched one Sputnik satellite, there was a lot of enthusiasm happening all around the world. So India also uh, woke up, and India also wanted to start the activities in space arena. In 1962, there was a committee formed by INCOSPAR, that is Indian National Committee Council for Space Research, and was formed. It was formed in 1962. There was no space department of then. There was the Atomic Energy Department. Under the Atomic Energy Department itself, the INCOSPAR committee was formed. And Dr. Sarabhai was assigned this task to take over the committee in Skopar. So 1962, we made a very humble beginning, and Dr. Sarabhai, he was very clear in his vision. So my first slide. I think slides, they are being presented from. Is it visible? Yeah, next one. First of all. Yeah. Dr. Sarabhai was very clear. His aim was India should be second to none in this application of advanced technology, space technology. Also, it has to address the real problems of man and the society. So that was his objective. So he wanted to make India uh, self-reliant in launch vehicle capabilities, also space satellite technologies, both in remote sensing and communication satellites, and relevant societal relevant application programs also through space. He wanted to do it. So that was his initial vision and the initial motive and objective. With that, he started. So first, he identified the apt place for doing these activities. So he went around all over India, and he identified a coastal village in near Trivandrum. That is, it's called Tumba. Tumba. So the advantage of Tumba was the proximity. It's a proximity to geomagnetic equator. That was the unique feature of this location. So this location was a very apt location to set up Tumba equatorial rocket launch station. So he set up Tumba equatorial rocket launch station, and it's called TERLS. Even today, the TERLS rocket launch station is existing. It is part of ISRO and the Vikram Sarabhai Space Center. So the vision of Indian space program when it was started was it was for mainly for national development, while pursuing space science and planetary exploration. Though INCOSPAR was formed in 1962, during 1969 only it was made as Indian Space Research Organization. So the over 7 years only it has become a regular organization. The activity started in 1962. Then the after identifying these turtles and establishing a launching station, first next slide. First rocket was launched during 1963. That was during November 21st of 1963. It was a sounding rocket. The sounding rocket also it was an imported rocket. It was called a Nike Apache. The Nike Apache rocket it was imported from Russia, and the launch was carried in turns. That was the first sounding rocket that made history for India. Uh, First rocket launch happening in Indian soil. Normally, the sounding rockets are meant for taking measurements along atmospheric studies or atmospheric conditions, lower atmosphere, middle atmosphere, upper atmosphere. The atmospheric temperature, weather, or for all these measurement to take these measurements, the sounding rockets are used. Also, it is used for making scientific experiments. Over the years, we have made many sounding rockets, but the beginning during 1963, the Tumba, the Dr. Sarabhai, he he sought the support of the coastal area leaders, the Christian community leaders, and the church building they offered for carrying out space activities. That was the first place where the scientists who were the time recruited from all over the world. Indian scientists were recruited from all over the world. Dr. Sarabhai recruited a few of the eminent people going around the world. So they were sitting in this church building. So that was the workspace as well as office the time. Later, the same church building became a space museum. Even today, it is there in the coastal area of Tumba. It is there. It is a space museum, and a lot of exhibits are there. So you can see left side, they have a very uh, prominent photograph where the sounding rocket is being transported to the launch site by a bicycle. So that was the initial condition prevailing at that time. So no sophistication, very crude way of handling things, no infrastructure. So people were taking a lot of efforts to carry on the activities. So that was the spirit shown by the people that time. So next slide. Then India developed many sounding rockets. There are a number of Rohini series of sounding rockets were built by India. It was called RH-200. There are three, four variants were made: RH-200, RH-300, RH-300 itself, RH Mark II version, and the latest version is RH-560. So each variant has got different payload capacity and the altitude up to which it can go also. So all those things, I listed the different categories as well as the for example, RH 560, if you see, it can go up to 560 kilometers, and the payload it can carry up to 100 kilograms. So that is the highest capable sounding rocket. But that RH-560 now it is being used for conducting many other experiments also for developmental activities. Whereas RH-200, even today, regularly the sounding rocket is being launched from Tumba Equatorial Launch Station on a regular basis. I think every alternate weekly, bi-weekly, it is being launched. There are people, where visitors are also allowed on permission. So these activities are going on. So that was the first matured activity happening in ISRO towards the rocketry. Next, we have migrated to, or we have matured to the orbital, I mean, the operational rockets. Next slide. Next slide, please. Yeah. So here, there is previous. Yeah. Different launch vehicles we have developed or ISRO developed are being shown here. The first of its kind is called the Satellite Launch Vehicle, SLV. So SLV was the first operational launch vehicle India built. So from sounding rocket to next slide, I will show the difference. The sounding rocket to this operational launch vehicle, there are a lot of differences. So here, this can so the geosynchronous orbit, geotransfer orbit, there are different orbits at different altitudes. And the payload capacity of each vehicle is different. Initially, to start with, this SLV rocket, it was made during early 1980s or late 70s, 79, 80, the time frame. First launch vehicle, launch was a failure, and the second launch was a partial success, and the third launch we made a good success. And at that time, our Dr. Abdul Kalam was the project director of this SLV-3 mission. Later, he became president also. So that was the major milestone achieved in launch vehicle technology by India. So there we struggled a lot to learn many things, many technologies, and over the years it got matured also. Next version is called the Augmented Satellite Launch Vehicle, or ASLV. ASLV, it is similar to SLV, but there are minor major improvements carried out. Here also, both SLV as well as ASLV, the propellants only we used only solid propellants. Number of stages are different, height is different, and the payload capacity from 40 we could enhance it to 150 kg, and the lift of weight mass also from 17 ton it increased to 39 tons. So the main objective was to increase the payload capacity of the launch vehicle. So that was achieved up to 150 kilometers, 150 kg. at the low Earth orbit. Low Earth orbit is something around 500 kilometers to 800 kilometers. That is called the low Earth orbit. Then we went on to, okay, these are all, I'm coming in details in further slides. Next slide, please. Yeah. No, I was referring, the sounding rocket, the main difference between sounding rocket and an operational launch vehicle. If you see, RH 560, I told sounding rocket, it reaches 560 kilometers. Both the SLV and the ASLV also reaches only 500 kilometers. The payload capacity of ASLV itself is 150 kilogram, and SLV is only 40 kilogram. Whereas this RH 560 can carry even 150 kg also, 100 to 150 kg can carry. So the main difference is the velocity created over the because of the propulsion is it should be sufficient enough to put the satellite in a particular orbit. Otherwise, it will come back. Mm. Now, once it is placed in the defined orbit, if we gain the sufficient velocity, it can place the satellite in the particular orbit and it can revolve around the Earth. So the minimum velocity what is needed is 7.35 kilometers per second to put a spacecraft in orbit. So that much velocity is achieved only in either SLV or ASLV or PSLV rockets, not in sounding rockets. So that is the main difference. Sounding rockets, it will go, it will take measurements and it will come back. So that is the difference. Similarly, when we talk about interplanetary missions like Chandrayaan, Mangalyaan, lunar mission, Mars orbiter mission, Venus mission, and different missions, from Earth gravity, it has to go out. Then only we can capture either lunar orbit or Martian orbit or Venus orbit or whatever is needed. So for which we should attain a velocity of 11.2 kilometer per second. So once we cross the 11.2 kilometers per second, we can totally come out of this Earth gravitation pull, and we can escape from this Earth field, Earth orbit. So we can go away from that orbit. So that is the main difference. And the launch vehicle should provide the capability to achieve this velocity. That is the most important thing. Next slide, please. Yeah, as I was earlier mentioning, SLV SLV had a payload capacity of only 40 kg and it was going up to 500 kilometers. Whereas ASLV was having a payload capacity of 150 kilometers. And first SLV3 was the total success, and Dr. Kalam was the uh, project director at that time. The main difference between the SLV and the ASLV was SLV3, if you take it, both use solid propulsion, whereas SLV3 we use open loop guidance system. Open loop guidance system means there is no feedback control. So it was a open loop. So we wanted to reach some orbit in a particular way. So that was programmed and sensors were tracking that orbit and then something like called the autopilot. So it was going in that way only, open loop guidance systems only. Navigation system, a major improvement was done in ASLV. There we have gone in for a closed loop guidance system. So the closed loop guidance system, it gives the feedback also. So whenever it deviates from the defined path, it has got a corrective mechanism also. The feedback control is there, and the feedback controls is acting on that, and the vehicle will be brought back to the required trajectory. That difference was there in SLV and ASLV. Next slide, please. Yeah. Here, if you see, I have put both the PSLV as well as GSLV. Now, similarly, PSLV and the GSLV, there are some differences. Whereas PSLV, it is meant for Polar Satellite Launch Vehicle. It is Polar Satellite Launch Vehicle. And the GSLV is Geostationary Launch Vehicle. The difference is polar means it can inject a satellite in a polar orbit. Polar orbit is something north to south, around the Earth, north south. It is called the polar orbit. Same PSLE can be used for geosynchronous missions also. We are used for not only geosynchronous missions as well as geotransfer missions, as well as for even for interplanetary missions also. PSLE was used. It is a versatile vehicle, but when it was built, it was meant for polar satellite launch vehicle and the polar orbit for launching satellites in polar orbits. PSLV was initiated. So the difference between PSLV and GSLV is PSLV from compared to SLV and ASLV, where we used only solid propulsion, whereas in PSLV we have gone in for liquid propulsion. So the difference between solid propulsion, liquid propulsion, and the summer cryogenic propulsion is the main parameter is specific impulse. When we have higher specific impulse, it can give maximum more thrust, and it can take it for higher altitudes. So in PSLV, not only solid propulsion, we have liquid stage also. PS2, second stage is a liquid stage, and fourth stage again it is a liquid stage. Fourth stage, the advantage of having a fourth stage liquid stage is if there are any variations in all the three stages, first stage or second stage and third stage, finally the fourth stage, if it is more also, we can trim it, we can shut down the liquid propulsion valve and close it to the required level. If it is needed, it can be fired for longer duration and satellite can be injected in the precise orbit. So that advantage we get in last when we have a last stage as a liquid stage. So that's why fourth stage here again we are going for liquid stage. So the liquid stage, liquid engine development was a huge task. Over the during 80s, the liquid engine, liquid propulsion was development was a major activity. It was being carried out in ISRO centers. From PSLV, GSLV, if you come, when we want to go for a geosynchronous orbit with a considerable payload capability, then we should have a cryogenic stage. So cryogenic stage development was taken up during this stage time. But the GSLV, what we initially we planned is so that time cryogenic development. It's not a very simple task. It takes maybe a minimum of 10 years or 10 to 12 years time period. So we wanted to have a technology transfer from other countries. US we approached, they denied it. France, I mean Russia was ready to give it, but Russia was they agreed to give the technology as well as a few cryogenic engines also. But unfortunately, because of political the GSL missions, we used Russian cryogenic stages. But we had certain issues also. So since the denial of technology by other countries has made to make our own cryogenic engines, and ISRO put in a lot of efforts to develop its own cryogenic engine, and cryogenic engine for the indigenous cryogenic engine was developed, and it is working flawlessly even during 100th mission which was flown last week also. The indigenous cryogenic engine was used in GSLV. So that is the geostationary satellite launch vehicle. The geostationary or transfer orbit is nothing but Polaris. It is around 600, 500, or even up to 900 kilometers. It is called a polar orbit. Whereas the geotransfer orbit, it is called 36,000 rupees, 36,000 kilometers. We have to reach it. Actually, it has to be geosynchronous, means 36,000 kilometers circular orbit we have to reach. But none of the launch vehicles, even Ariane or any other vehicle, if you take it also, it cannot carry the satellite to 36,000 kilometer circular orbit. Normally, what is being done is it will launch the satellite only in geotransfer orbit. Geotransfer orbit means it is a highly elliptical orbit. The apogee will be 36,000 kilometers, whereas the perigee will be, it may vary from 180 to 240 or 270 kilometers depending on the launch vehicle capability. So that way, then from the elliptical orbit, this propulsion system, which is resident in satellite, will be used for making the orbit corrections. From 180 kilometers perigee to, it will be made to 36,000 kilometers. So that's how we reach 36,000 circular orbit, which is a geostationary orbit. Yeah, next slide, please. From GSLV, the next objective was to go for, though we have developed a cryogenic engine, the payload capability of GSLV was only 2 ton or 2.5 ton, 2,200 kilograms or something. But for a when we talk about the geosynchronous satellites, it is mainly used for communication satellite. The communication satellite, normally 3,000 to 4,000 kg satellite only it is being planned. That is only viable because we need to, it has to work for long years, 10 to 15 years. And the propulsion system itself is taking off of the satellite mass. So the real payload transponders capacity will be limited. That's why to make it viable, the satellite mass has to be more than 3 ton, 3.5 to 4 tons. So unless we augment the launch vehicle capability, we cannot be able to achieve this 4 ton payload mass. So we have gone in for LVM3, GSLV Mark III vehicle. GSLV Mark III vehicle, it's again uses the strap-on system, strap-on boosters. It's a solid boosters, and the main first stage vehicle is the first stage of the vehicle is a liquid engine. It's a twin engine, and the upper stage is a cryogenic engine. But everywhere the silent propulsion, liquid propulsion, as well as the cryogenic stages, the performance, rather the capacity is enhanced. So that was the cryogenic stage also. Here we have higher capacity, and the solid booster also it is S200 when compared to PSLV or ASLV. The solid booster capacity is very high, and it produces huge thrust. So with this, we could take 4 ton satellite to geosynchronous orbit, or for low Earth orbit, this can be used for 10 ton capacity. 10 ton capacity. So normal mission definition, I put it as I mentioned earlier. Perigee will be around 180 kilometers, and apogee will be around 36,000 kilometers. So that was the nominal orbital parameters we get from GSLV Mark III. And the operational first satellite GSLV Mark III mission was it has taken place during 2017. So here the augmenting the cryogenic stage, even solid boosters, It's a huge task, and over the years, it has matured and it has become a very successful operational vehicle nowadays. So this vehicle is being uh, augmented for mandating to take human being also further. Next slide, please. As I was mentioning, the over the from SLV to uh, LVM3 vehicle, the technology progression in various areas, technology domains, it is tremendous. Liquid propulsion, if you see, large boosters were developed, the upper stage, liquid upper stage was developed, a heat shield also, bulbous heat shield, bulbous heat shield that can help, that will be helpful for to get better aerodynamic characteristics as well as to accommodate higher diameter spacecraft. And avionics, we had done a lot of improvements, and then navigation system, guidance, structures, everywhere, lot of improvements were carried on. And as I was telling, closed loop technology in ASLV itself we used, but that was a gimbal platform, whereas the PSLV used for strap-on technology. And we built a second launch pad in Sririkota to take care of these launch activities. Now, third for building a third launch pad, approval is government has given the approvals. So these are all the technology progression made over the years, the last 3 decades. Next slide. This is one of the important marvelous development achieved by ISRO is the cryogenic stage development. As I was mentioning, the technology was denied, and we developed our own cryogenic engine as well as technology. The stage development was carried out, and it is giving flawless performance for the years. And detailed, we have done a number of qualification tests. Uh, and for doing this test, a lot of test facilities were established in Mahendragiri. So it was a great achievement made by the ISRO organization. Next slide. So launch vehicle, this is a space capsule recovery experiment. It is space capsule recovery experiment is one of the historic event made by ISRO. So this is, I would say, it's a precursor for a human mission or manned mission or re-entry vehicle. So the space recovery experiment, what was done is the satellite, it was carried. It has it was there in the orbit for 3 days, a few days, and it has made some experiments, measurements. Then the the capsule was deboosted. It was deboosted to re-enter the Earth again, and it came back to Earth. It landed on the uh, sea. So this experiment was done during 2017 January, and it was successfully recovered, and it was one of the major milestones achieved at that time. So this has laid a foundation for reusable launch vehicle, manned mission, as well as for future sample return missions. What we are envisaging and talking about in the next decades. Next slide. So I have given more details on this SRE mission. So the rocket carried this space capsule. Space capsule. It was launched like any other satellite. It was there in the orbit for a few days. It has done some microgravity experiment and other some of the experiments. Then the space capsule was deboosted. Deboosted in the sense it was fired in other direction. So it started its journey to re-enter the Earth. So the re-entry started. The major issue is during the re-entry, the velocity of the vehicle capsule will be very high. What we need is the main objective will be to reduce the velocity uh, uh, to great extent to land. So that is one of the things. Because of this velocity, lot of heat will be produced. So the thermal protection system will be very important. So the thermal protection system is given by the tiles fixed on the outer surface of the capsule. So the thermal tiles, those things were developed during this mission. Even you may be remembering one of the American vehicle at the time of re-entry, because of one thermal tile debonding, total vehicle was burnt off and the astronauts had a, I mean, they could not survive also. So such a important thing, the tail, the purpose it serves. In the temperature will be of the order of more than 2000 degree Celsius, 2400 degrees Celsius. It has to withstand that temperature. The inside the capsule, the temperature should not be transmitted. Otherwise, all the systems will burn off. The tails have to protect that temperature. So that was the important thing. So to reduce the velocity, two, three stages of parachutes were used. It's called a drag chute, main chute. So the velocity from 8,000 meter per second to it was reduced to some 12 meter per second. Then at the time of touchdown, almost okay, zero velocity touch to turn. So 12 meter per second, it will make the touchdown in sea. Maybe for human mission, we cannot land in sea. We have to land in on the ground. So this criticality lies in human mission also. More important thing is the human safety also we have to take care. So there, this that gives a lot of challenges also. So this was a precursor for human mission also. Next slide, please. Then next one major milestone achieved was reusable launch vehicle. Reusable launch vehicle is it is gives more economical. Same vehicle can be multiple times it can be used, but it's a technologically challenging endeavor. Developing essential reusable launch vehicle technology in itself is a challenge. Uh, Obviously, it becomes a cheaper version, a cheaper option. The reusable launch vehicle was configured in such a way that it will go like a launch vehicle and land like a aircraft. So that was the configuration we planned, and it was successfully developed. And number of times, recent times also, you would have seen reusable launch vehicle was successfully it has landed. Three, four trials were made, and so every time we got successful re-entry also. Same reusable launch vehicle with air breathing propulsion also can be done. So while going itself, the air breathing engine will intake the oxygen from atmosphere. It will be that will be compressed. That air will be compressed, and the compressed air will be get into the fuel injection mixed with the injected fuel, and it will expand and give the thrust. So that's how this is functioning. This is another cheaper configuration. It is being worked out. Next is Gaganyaan mission. Next slide, please. Next slide. Yeah. Next launch vehicle, if you see, the major milestone to be achieved is Gaganyaan. Uh, as I mentioned, the LM-3 vehicle, it can carry a payload of spacecraft of 10,000 ton. See, Gaganyaan mission normally launch a human mission. We are not going to very high orbit. Normally, it will be around 300, 400, 300, 400 kilometer orbit. So for carrying 300, 400, taking to 300, 400 kilometer orbit, even 10,000 ton or more than 12 ton capacity this LVM-3 vehicle can carry. So only challenge is the LVM-3 vehicle has to be manned rated. Manned rating is a different ball game altogether. For normally launching satellites, we have certain margins and we are taking care. Where when we carry human being, human safety is paramount important. So human safety means totally should be failure safe, failure proof. So we need to, in case of any eventuality, the crew should be able to escape. So crew escape system has to be built in, and the crew model has to be separated from the service model. Service model will be the operational activities will be happening, whereas crew model will be it's like a habitat. Human should be able to survive. It should be temperature, weather, pressure, all the things should be comfortable for the human beings. So for such things also, we should be able to do certain scientific experiments also. The crew model has to be configured like that. The Gaganyaan mission, it's planned to the mission duration. It's planned for up to 7 days initially. 7 days. Any event to take care of any eventuality. Mission abort and the crew rescue provision should be made available. And crew model is designed for re-entry and a service mission, a service model for mission management. These are all the configuration requirements of the Gaganyaan mission. It is very actively pursued right now. Next slide, please. So next, the objective will be to reach moon and come back. Human has to go to moon and come back. That will be the futuristic development. It is okay initiated right now. I would say now 20 up to 2047 the roadmap is made for a space program. So these are all coming under that. So for reaching moon, for carrying human being to moon, the existing launch vehicle may not be able to cater to the requirement. So there we need to have more, I mean, heavy lift launch vehicle. Heavy lift launch vehicle in the sense, instead of 10 ton, we should be able to carry more than 20 ton or 30 tons. So that can be achieved not with the existing configuration. There we may have to go for semi-cryo engines also. So semi-cryo engine, the R&D research and development activities are going on right now. And in the next few years, we'll be able to demonstrate a semi-cryo engine. And the vehicle configuration is also finalized. It is called NGLV or Surya. It is named as Surya new generation launch vehicle, new generation launch vehicle with a semi-cryo engine. It is one cryogenic fluid and another one will be, it is a methane, liquid oxygen, methane will be the propellants. So there we will be able to achieve the requirements. Even up to 19.2 kilometer per second, we will be able to achieve. The lunar payload we will be able to carry around 20 tons. This was the whereas GSLV Mark III, we have limitations. Only 4 tons will be able to carry. So we are necessarily we have to go for new vehicle, and the development activities are being actively pursued. Next slide. As I mentioned earlier, the manned mission, the a host of new technologies need to be developed. As I was telling, crew escape system, also space suit and the crew seat. Space suit, the space suit, each vehicle has got specific or customized space suits. You would have come across news in Sunita Williams struck in space, because the vehicle which carried Boeing, which carried that carried the astronauts to space. The space suits for suitable for Boeing is not suitable for many other vehicles. So such constraints are prevailing for space suits. So for Gaganyaan mission, we have to have our customized space suits. And the robust thermal protection system, as I was during SRE, I was mentioning, the thermal protection system should be robust. On any condition, the thermal protection should not be compromised, cannot be compromised. That will totally destroy the vehicle otherwise. And the crew always, the health monitoring system is a inbuilt facility to be established in the vehicle. As usual, mission management and human in loop with the human in loop. Normally, for launch vehicle, mission management is being done. When the human is also there, the mission management accordingly it has to be customized. And mandating of launch vehicles. Launch vehicle, normally we will have certain critical systems. We will have redundancy. Redundancy in the sense, so in case there are a few sensors, very important sensors, if one sensor fail, this launch vehicle, total launch vehicle should not be in problem. So normally we will have another redundant sensor also in loop. Or if one sensor fails also, we'll be able to manage the mission. So that is called a redundancy. But there is with a single redundancy, triple or quadruple redundancies are planned for mandated vehicles. So even two sensors or two systems fail, the vehicle should not be in a problem. So that is called triple redundancy. Quadruple means three, four, totally four options will be available. Even three, by chance, three options are failing also, fourth option will be there to take care of the system. So such depending on the criticality, such a redundancy management is done for mandating of the vehicle. Also, the crew has to be trained. Crew training is very important. Right now, we don't have much facilities. Only aviation training, military, air force facilities are available. But mainly, we are getting support from other countries for training our crew. Also. And manned space vehicle simulators and environmental control life support system. These are all new facilities and new systems that will be established for manned mission. Next slide, please. So from sounding rocket up to this manned mission or beyond human carrying a human to moon also, there is a plan or the activities are going on. I covered that. Next I will come to satellite side. So satellites, in astronomy, satellite is a body which is orbiting around a planet. There are natural satellites. We know Moon, Venus, these are natural satellites. Man-made artificial satellites are also. there are a number of satellites we know, remote sensing satellites, communication satellites, and so many other space stations. All are satellites only. Next step. Next slide, please. Like a sounding rocket. So satellite side, if you take it, this one Aryabhatta was the first satellite in 1975. It was launched by India. It was launched from other country only, Russia. It was named after the astronomer, Indian astronomer. This was built to conduct X-ray astronomy, aeronautics, and solar physics. So this was the first satellite to be built by India. Next slide, please. And the early satellites we called like after Aryabhatta, there was Rohini, which was launched by SLV. SRS, that is Stretched Ray Rohini series. Bhaskara is also another satellite. Satellite launched by from outside India. And Apple was these are all scientific satellites. It is only experimental satellites. It's not operational satellites. To to demonstrate our technology, whatever we have developed, to demonstrate that the satellites were built and demonstrated. And the next we have gone in for Apple is a communication satellite, experimental communication satellite. Whereas Aryabhatta and Bhaskar are remote sensing satellites, experimental remote sensing satellites. Then we have gone in for operational remote sensing satellites like IRS, ResourceSat, SCATSat, and so many satellites we have launched. And a host of satellite remote sensing satellites were launched by India. Similarly, Indian National INSAT, GSAT, these are all communication satellites. I'll come to that. Next slide. Yeah, satellites are there are different types of satellites. Mainly, the human being mainly widely used one is communication. The communication total it has breakthrough has happened only because of the satellite communication only. This broadband, telephone, mobile, all those things. This revolution has happened because of the satellite communication. Then there's remote sensing. Remote sensing is from distance you are imaging. It is taking photographs from orbit. That is for studying so many things for weather, sea conditions. You can study agriculture, um, underwater. For different applications, this remote sensing satellite can be used. Navigation satellites. Navigation is nothing but like what we use GPS. We have Indian navigation satellite constellation, Navic. Indian constellation we are building up. So that is used for navigation purpose. Which is being used now. Everybody is mobile. It is available. Of course, we are using GPS receivers, GPS signal. Shortly, we will be able to migrate it to Navic. Then for atmospheric studies, for weather predictions, scientific applications, astronomy, space exploration, space experiment. For different applications, satellites are built and launched. Excellent. Here, just yeah, some of the satellites are remote sensing. If you see AstroSat, TWSat, SRAS, Chandrayaan, Megatropics, these are all OceanSat, Cartosat, RISat. These are all remote sensing satellites. Similarly, communication satellite INSAT series, INSAT 1, 2 series. INSAT 1 series was satellites were built by Ford Aerospace. on Indian design, and they launched for us. Whereas INSAT 2 series onwards, India built our own satellites and it launched. The transponders were totally indigenous thing, and it was used for communication. And the communication revolution happened only during that time. The telecom and broadband communications. Of course, GSAT also similar purpose it is serving. IRLS is navigation for navigation. It is being used. Then scientific missions are there. Some of the satellites are being used. Next slide, please.
Hello, good evening. Good evening.
Yeah, the communication satellite. When you come to communication satellites, everybody knows satellite communication now. It is being widely used. But the communication satellite, the main thing is the satellite will be launched at the altitude of
Are you studying or not?
36,000 kilometers.
Because from last
36
2 3 days,
36,000 kilometers. 36,000 kilometer. Why the significance is at the 36,000 kilometer, the orbit, the satellite takes 24 hours for rotating for one rotation. So it is synchronous to Earth rotation. That's why it is called a geosynchronous satellite. So because of this, for communication, the satellite has to face the India means always it has to face India or any globe, any part of the world continuously on the from the same place. If the satellite is moving, communication may not happen properly. So, with respect to Earth, the satellite is it is in a fixed condition. That's why it is called a geosynchronous geostationary satellite, and it is at 36,000 kilometers orbit. So, with one satellite, we will be able to cover reasonably large part of the Earth. So, with the one satellite, we will be able to provide communication communication for different application for different part of the country as well as world also. So that is the main advantage of this communication satellites. Next slide, please. Next is remote sensing satellite. Remote sensing satellite is mainly for taking imageries. So it is launching normally in polar orbit. Polar orbit, earlier as I mentioned, it is in north-south direction. The satellite will be rotating, and Earth is rotating in the west to east. So from the satellite, it will be able to take a picture of Earth in a large area. It will be able to take the imagery of the Earth. So that is the advantage, and that's why it is. Polar orbits are preferred for imaging for remote sensing. So these satellites will be launched at an altitude of 500 to 900 kilometers, depending on the requirements. So closer the Earth, the imagery will be, the sensitivity will be better. Okay, depending on the application, the orbit will be selected. Um, uh, and different applications are there. Even for forestry, we are using, for agriculture, we are using, for environmental oceanography, we are using. Different remote sensing applications are there. For different satellite, same satellite does multiple applications also, as well as for individual application, we have individual separate satellite also. So all these possibilities are there. Next slide, please. Then one of the major application we have launched a especially exclusive satellite for education. EduSat, it was called EduSat. The EduSat program, the eminent teachers from a classroom at one location that their classes can be transmitted to many rural areas or remote places also. So that was the advantage. So from teaching end, the signals will be transmitted to the from the antenna will be transmitted to the satellite, and from the satellite again it will be received to the classrooms in remote places through the antennas. So that was the main advantage in the education sector. So that was very useful for serving, yeah, for getting a very quality education for rural as well as remote places. Place. Next slide, please. Similarly, similar to educate, telemedicine also it is possible. Expert medical advice, medical even surgical procedures can be guided by experts from remote places or from abroad via through satellite in maybe local hospitals also if we make the setup ready from satellite telemedicine they can get the signals even from the very maybe for from US also you can get doctors consultation as well as even for guiding that surgery also he can give instructions and a local doctor will be able to perform all the activities from their theater or their room. So that was also feasible through this telemedicine facility which was provided by the satellite. Next slide. Next is meteorology. It is, of course, everybody knows for weather forecasting, cyclone prediction. These are all very essential things. Earlier, we used to, along with the communication satellite, this VHR, high resolution cameras and charge coupled device cameras were flown, and like InSat 3D satellite. Right now, even that is being used for weather forecasting. Even a few years back, this Odisha cyclone, because of this satellite imagery and a warning, we could save a lot of life by this alert. They could take care of, they can move the people from the uh, critical areas. They could save the people. Next slide, please. Next is IRNS series of satellites. And this, as I was mentioning, it is used for navigation purpose. The GPS satellites, GPS receivers, it is widely being used everywhere. Your mobiles, automobiles, everywhere GPS signal is available. But even for launch vehicle, also this is being used. But one issue is whenever there is when US decides to block the signal, they can anytime they can block it. At critical moment when you need it, they can block it or they can jam it or they can send some false signals also. So better as a developed country, we need to have our own constellation of satellites which provide this navigation, which can be used for navigation purpose. So this is also is launched in the geosynchronous orbit or geotransfer orbit. Yeah, constellation of satellites. IRNS is it is a Indian regional navigation system. Entire India, it will have a coverage. That is the objective of the system. Minimum of seven satellites are planned. It is working on the seven satellites are working. So with the Navic receiver, we will be able to even GPS signal is not there. We will be able to with the manage with the Navic signal. It is the quality of the signal or the precision or accuracy of the system is as good as GPS also. We will be able to maybe Mavic receivers are not available right now in a smaller size, which can be customized or which can be built in your mobile or automobiles. Maybe over the time that can be done, receivers can be made and these satellites can be used for to totally replace the GPS satellite. Next slide. In satellite side, launch vehicle, we have seen different propulsion system. But satellite side, there is one important system for propulsion, electric propulsion. Electric propulsion is a space propulsion which makes use of electric power to accelerate it. See, now we are seeing automobiles, EV vehicles. Instead of using petrol or diesel, we are using electric motors for driving our two-wheelers or four-wheelers. Similarly, for instead of using propellant, chemical propellant, electric power for giving the thrust in satellites. So that is the basic concept. But electric propulsion compared to chemical propulsion, lot of some differences are there. But for over long duration, with the electric propulsion, we will be able to achieve very good maybe payload capability and things. Next slide. Next slide, please. So just to have a comparison, liquid rocket, liquid propulsion is normally it is being used. The specific impulse, ISP, what is called as liquid propellant, it is 450 seconds. Whereas for electric propellant, it is 3000 seconds. Whereas the thrust, if you see, it is what we get is very small thrust, 0.1 Newton or that sort of number only we get it. Whereas electric propulsion, the thrust will be in kilotons, kilonewton or meganewton. That sort of thrust we get. Whereas this electric propulsion, if you take a communication satellite, more than 50% of the satellite mass, what is if you take 4000 kg satellite, more than 2000 kg will be electric, I mean chemical propellant only. After raising the orbit, if you see, when it reaches the geosynchronous orbit, the mass of the satellite will be only 50%, 2000 kg only will be there. So rest of the propellant is exhausted for raising the orbit. The advantage of electric propulsion is the instead of for 2000 kg using it for propulsion, the mass of the electric propulsion system will be very small. More than 1500, we will be able to carry the transponders, useful transponders, which can augment the communication capability. The only thing in chemical propulsion, we will be able to reach the orbit in few days. Whereas electric propulsion, it will take a few months. But still, when the satellite is working for 15, 20 years, few months or few, it will not be able to, it will not be going to make much of difference. So the satellite mass or the transponder with the liquid propulsion, if you are carrying some 50 transponders, with electric propulsion, we will be able to carry 100 transponders. So that is the main advantage of this electric propulsion. And electric propulsion development is actively pursued. And next year or this year, the demonstration will be done. Earlier, to a smaller extent, it was done it was experimental, and now major activities being pursued. Next slide, please. So this is interplanetary mission. Satellite is communication, remote sensing, all these things are covered there. Next is interplanetary mission. So Chandrayaan mission we have taken up during it was launched during 2008. It was a grand success. So this Chandrayaan one only the Indian national flag was planted in moon surface by this during this mission, and this mission was used to find the water samples, water molecules in the moon surface also. Next slide, please. The main difference is when we launch up communication satellite along the remote sensing. Remote sensing is directly the satellite will be placed in orbit. The communication satellite geosynchronous, it will be placed in geo transfer orbit, and then it will be raised to geosynchronous orbit over for 4 5 days. Whereas in Chandrayaan mission, from geo transfer, the satellite will be launched in geo transfer orbit. Then it will be moved to Earth transfer orbit. Then it has to, as I mentioned in the initial slides, the escape velocity, it has to go out of the Earth field, Earth orbit, and you have to get into the lunar orbit. So that is a lunar transfer trajectory we have to get into. Then lunar capture has to take place. Lunar injection, orbit injection has to be done. So these are all the mission criticalities and the sufficient propellant and the accuracy of the sensors because the real-time communication with the satellite may not be happening. So we will have some time blockage. The signal will take reach to satellite as well as to come back to Earth may take a few minutes. So the autonomy of this satellite has to be built inside, and the sensors, the propulsion systems have to be very precise to achieve this mission. Next slide, please. Next is Mars Red Planet, Indian mission to Mars orbiter. Next slide. Next slide. Yeah. So we made a grand success in the Mangalyaan mission. So here also, like a lunar mission, the mass of the satellite was around 1,400, 1,350 kilogram only. The cost was only less than 500 crores at the time, and it was very. And we used the PSLV to carry this Mars orbiter mission. PSLV is the I'll give to have a feel of it. I'll give comparison of Mars mission taken up by US at that point of time. So just you'll see that. So 2014 we achieved this mission. So this mission helped to place India in a very strong position in the space arena, and many developed countries their outlook towards India changed after this mission. So that way it was a great mission to achieve. Yeah, next slide. Yeah, when India planned their Mars mission, uh, Russia, I mean US also, there was a Mars mission. They used Atlas V401 vehicle. We used a PSLV vehicle, and the launch um, the they can carry more than 10,000 kg to Leo orbit, whereas the payload capacity of PSLE is only 1,600 or 1,700 kg in Leo, I mean polar orbit. And the GTO orbit, it is only 1,000 kg. GTO orbit, whereas Atlas vehicle can carry 4,750 kg. So that was the order of difference between the US vehicle and our vehicle. But still, we made it a successful mission. Next slide, please. As I mentioned for lunar mission, here also the from the launch to getting into Martian orbit, it took more than 9 months. The launch took place in November 27th of 2013. We got into Mars orbit in September 24th, 2014 only we reached the orbit. 2014 only we reached. So for more than 9 months, nearly 10 months it took to reach the Mars orbit. So here also from GTO we have earthbound transfers. So multiple times we have to raise the satellite to different orbits from earthbound to Martian transfer trajectory orbits we have to go. Then we have to go for Martian orbit injection. So over 9 to 10 months, the satellite was continuously tracked and the orbit was raised. By every time the performance of the propulsion system, sensor system, everything was very critical and everything was working very flawlessly. We had a lot of challenges compared to Chandrayaan, Mars mission. We had a lot of challenges also. I'll come to that. Next slide, please. Again, the comparison, if you see, the Maven, which was launched at the time, the mass was 2,500 kg. Yeah? And it used 200 Newton thrust. Maven used 200 Newton thrust. We of 6 motors, 200 into 6 motors, 1,200 Newton of thrust, whereas we had only 440 Newton thrust, thrust motor. So that was the difference with this. We managed the mission and it was very successfully achieved also. Next slide, please. I was referring to challenges. The main thing is the communication. Communication, the orbit, the Martian orbit, when they compared the satellite altitude was, it was around more than 200 kilometers to between 200 to 400 kilometers, 200 million kilometers to 400 million kilometer distance. So you cannot imagine the distance. So that much high distance was there. The accuracy requirements for orbit prediction was very critical. Uh, we have to really assess the exact orbit. Then only we can move it to the required levels. So that was also the communication at this 400 million kilometers was a huge task. We built a deep space network during Chandrayaan time itself that was enhanced during Mars mission. So deep space network communication system was only working. Also, we took support from other agencies also. And spacecraft autonomy was one of the main paramount thing because as I was mentioning, the signal to travel from ground to satellite and satellite back to ground, it was taking as high as 40 minutes and all, sometimes more than 40 minutes. So the 40 minutes, everything will be over. Everything will be over. So what is needed is the satellite. When we program it, the satellite activities have to happen at the time tagged manner, so that the planned way, the Mars capture has to on a particular day, particular time only it has to happen. Otherwise, we'll be going away from the Mars orbit, Mars orbit. So if we miss that, the opportunity will be lost. Will be nowhere. So that was a very critical thing, and autonomy was built within the system. Not only autonomy, the system, sensors and the systems have to function properly. Otherwise, the precision at which the sensors were measuring was marvelous, and that helped to achieve these accuracies. And another important thing is the thermal and radiation, because of the at this altitude with the varying temperatures over 300 days, all the systems have to function perfectly, so that it has to work flawlessly. Next slide, please. Another important challenge was the propulsion system. The 300 days, the first initially propulsion system will be used for the LAM engine will be major LAM engine will be used for initial days. Then it will not be used. Then after 300 days, at the extreme temperature, it will be undergoing, and it has to when we wanted to inject the into Martian orbit, it has to function properly, and there should not be any leak. If any leak happens over the time 300 days, all propellant will be lost. So such a criticalities were there, and even your automobile, your car or two wheelers, if you don't take it for 1 week, then you may find it difficult to start the engine. So here it has to work for 300 days like that. Mm. So there was a huge challenge. And the redundancy management for propulsion system was also planned, and it was done. And power systems also, solar power, not like other orbits, will be able to generate the solar power. Unless they have solar power, the systems may not be able to function also. They cannot get sufficient power to operate. So, so that was also very critical. The temperature, solar panel temperature was going as low as minus 185 degrees. So all these challenges were envisaged, planned, and executed meticulously, and we achieved a great mission. Next slide, please. So we are expanding this our space endeavor through over the years. I have okay, detailed way I have already given from 1963 to 2025 we achieved. Then after 2025 also now we have roadmap for up to 2047 it is planned. Next slide, please. The latest one to achieve is the space docking mission. It is again a precursor for the space station. We are planning more like Russian space station. We are planning Bharati Antariksha station. So that activities are started for that this docking mechanism docking has to be perfected. So we have launched two satellites to experiment that docking phenomenon. And there was a two satellite. One is called target satellite. Other one is chaser satellite. So it was achieved perfectly, and India was the fourth country to achieve this docking mission. Next slide, please. So this gives a detail. So the satellite mass to each satellite was 220 kg. It was put in 70-kilometer orbit. But initially the satellites were traveling at a 20,800 kilometer orbit, 20,000 kilometer per hour speed velocity, which is 36 times of our commercial airplane velocity. So from that we have to reduce it to very small velocity, almost zero, to achieve this docking. We have reduced this velocity to 10 millimeter per second, then mated together. After mating, the latches, the mechanism, docking mechanism was made to operate, and the latches were engaged, and the docking was made perfect. Also, this docking also there are standards prescribed by NASA, and this Bharati docking system, which meets international docking system standards also. So that is the main highlight of this mission. Next slide, please. Next, we are aiming for lunar sample return mission. Chandrayaan 3, we have gone in. Chandrayaan 3 was recent thing, and Chandrayaan 4 is lunar sample return mission. So here the on lunar surface we have to land. We have to remove extractors, and lunar sample has to be collected, and it has to be put in container. And after containerization, this sample has to again come back to Earth. So, a lot of activities, a lot of technologies are involved. Not only docking, undocking, and from moon surface, it has again it has to take off from moon surface, transfer sample from one model to another, again return and re-entry to Earth for sample delivery. So these are all the critical technologies to be developed. It is planned during 2028 or so. So the activities are going on. Next slide, please. Finally, this we are working on Bharati Antariksha station. The developmental activities are just started. So first, there will be 5 modules. First model of the for demonstration is planned to be launched by 2028, and a full-fledged station operational station is planned by 2035. Next slide, please. As I mentioned, it will have 5 modules. The dimension is the length of the model will be 27 meters, 27 by 20 meters, and the maximum crew capacity planned is 6 astronauts. It will be orbiting around the 400 to 450 kilometer orbit. So the 5 models are mainly base model, core docking model, science research model, laboratory model, common working model. So each model can independently be launched. It can go to the will go and dock with the base model, and then will form with the 5 models. It will form the total entire station. Next slide. So next ambition is colonization of Mars. So we hope one day we will achieve this colonization of Mars. Previous slide. Okay, it is previous slide was okay. So we let us hope we will achieve this one day. Next slide, please. So I will conclude with this slide. Over the 4 decades, when we started from the scratch, over the 4 decades, so recent launch, what was previous launch was made was a 100th launch vehicle mission, and we have launched 128 satellite missions, and self-sufficiency we are achieving satellites technology, launch vehicle technology, and interplanetary missions also we have achieved. So we are marching towards further developments. So we are fulfilling the dreams of Dr. Sarabhai. That is the achievement made by the ISRO. So this is how space program has evolved over the 4 decades, 4 to 5 decades. That's all. Thank you. Thank you for everybody. Thank you for patient listening. Thank you. That's all from my side, sir. Thank you.
Thank you, sir. Thank you, sir. Participants, any queries? So, on behalf of Markandam College of Engineering and Technology and all our participants, I would like to extend heartfelt gratitude to Sri M.S. J. Chandran, former Deputy Director, Reliability and ISRO Internal Systems Unit, Trivandrum, for sharing valuables and knowledge during this online FDP program. Your engaging presentation also provide us valuable knowledge. Your contribution made a significant impact on our learning journey. We are grateful for the clarity and passion with which you presented the different types of satellites. Hope today's session certainly left lasting impressions. Once again, we thank you, sir.
We now move forward to our
Thank
next.
you. Thank you.
We now move forward to our next session. Session 2 focuses on quality ruling space. We are honored to have our esteemed speaker, Sri Adi Bhagavan, former group director and quality assurance in Indian Space Research Organization for this session. With over 35 years of experience in quality assurance of inertial systems for spacecraft applications, Sri Adi Bhagavan brings immense knowledge and expertise to this topic. His expertise is backed by an impressive portfolio of research, having presented numerous papers in national and international conferences on quality. He has undergone tribal. Besides, he finished a 2-week quality circle training at Bharat Electronics Limited, Bangalore. He was deputed to French Guiana for the INSAT launch campaign. His dedication to excellence is evident in his accolades, including the prestigious Team ISRO Excellence Award and his victory in the process quality competition held at ISRO, Ahmedabad. Further solidifying his leadership in the field, he serves as the chairman of the National Institution for Quality and Reliability, where he continues to drive innovation and uphold the highest standards. Tonight, he will be sharing his insights on quality ruling space. Over to you, sir.
Good evening to all. Are you able to hear me?
Yes, sir.
Okay. So, I think I can share the screen. Are you able to see the screen? Hello?
So we are able to see you, not the screen.
Screen you are not able to see. Okay, 1 second. This area. Okay. That way.
ஷேர் ஸ்கிரீன் ரெண்டாவது இங்கிட்ட அப்லோட் ஆகல அது
இதான் இருக்கா?
கிளிக் பண்ண வேண்டியதானே இப்போ பிபிடி
வரலையா?
பிபிடி டபுள் கிளிக் பண்ணுங்க அந்த லிங்க் இருக்குது இனி அந்த லிங்க் எழுதிட்டு வலையுண்டு
இதான் இருக்கா?
இது க்ளோஸ் பண்ணுங்க அந்த லிங்க் வரலையா ஷேர் பண்ணுங்க இதில் வேறு எங்கேயாவது ஷேர் இருக்கா அந்த இடத்துல என்ன இருக்கு
Render screen. Cancel. Okay.
லிங்க் கிளிக் பண்ணுங்க
Okay.
ஷேர்
Okay, now are you able to see?
ஷேர்
Yes, sir.
You are able to see? Okay.
எஸ் சார்
Hello?
Sir, can you go to full screen mode?
Okay. Full screen only I have put.
Okay.
Okay.
Hello, sir. Slideshow. Can you go to slideshow?
States.
ஸ்டாப் ஷேரிங் ஸ்டாப் ஷேரிங்
1 second.
ஸ்லைட் ஷோ
Now?
Yeah. It has gone back, sir.
Escape हो गया
Slideshow from beginning ஏதாவது இருக்கா?
Start from beginning. இல்லையா? Escape பண்ணுங்க. Okay. Now you are able to see?
Yes.
Hello?
Yes, sir. Yes,
Yes, sir. Yes, sir.
Yeah. Okay. Okay. Good evening again. Good evening to all. The quality is a strange thing which we will be thinking only during its absence. One small example I will tell. We all know about Vande Bharat and we are happy to travel by Vande Bharat Express. Suppose one day there is a delay of 5 or 10 minutes, so immediately we will be blaming that Vande Bharat is not keeping that time. So that time only we will be thinking about quality. So like that, when there is a problem, then only we will be thinking about quality. So this is the peculiar character of quality. You will feel its absence. So that is quality. For example, you are going to a restaurant. You are ordering a food and it is good and you will come out. Maybe famous hotels like A to B, Saravanan, etc. Suppose the food quality is bad, immediately we will comment and we will forget about the quality of food which we have tasted during our earlier times. So this is the thing. When the particular thing, when there is an absence of quality, then only we will be thinking about quality. So this is a peculiar characteristic of quality. And this quality is having a lot of definitions. The three words: customer satisfaction, sustainability, and reliability. These three are the main words of quality. So customer should be satisfied. So it is mainly applicable for service related organization. And sustainability. This is what the example I have told. If one day the train comes late, we are blaming. So we should always keep the time. So that is important. So that is called the sustainability and reliability. So it is the repeatability of the process. So it should be reliable. If your product is reliable, means there should not be any problem over a time period, say for 5 years or 6 years. So there is a rated life for any system. So within that time period, the system should function. So that is called reliability. So these three are the main mantras of quality. And the most distinctive attribute or characteristic possessed by someone or something. The quality is not it is applicable to product, not only product, but also the human being. So now I am going to discuss about the quality of the human being. So leaders. So human being means for any organization there will be a leader. So the leadership quality is very important for the success of any organization. And ISRO, we are fortunate to have quality leaders from the beginning, starting from Sarabhai and up to the present chairman, Dr. Narayanan. We are blessed to have quality leaders. And subsequent, I mean, after the untimely death of Sarabhai, Professor Dhawan took over the mantle. So you can see in the right hand side picture. Hello, are you hearing? Shall I continue?
Yes, sir.
Okay, okay. In between some disturbance came. That's what somebody is asking something. Okay, now the right hand side picture, if you see, the person in the middle with the blue shirt is Professor Satish Dhawan, and he is responsible for building ISRO to a greater height because he is the only chairman who has served a long period in ISRO. So during his period only, ISRO got many sectors, many technologies were being developed during Professor Satish Dhawan's period. It is, we can say it is a golden period for ISRO. And in the right side, you can see a man with a file. So he is Dr. Abdul Kalam, and he is from the rocket man who elevated to the President of India. So one of the main leadership quality, just I want to quote from their incident, it was the first attempt of SLV. So it was you all know it was a failure. And Professor Satish Dhawan was the chairman of ISRO at that time. So press people are eagerly waiting. So he immediately came out and he told, as the chairman of ISRO, I take the responsibility. I own the responsibility for this failure. And next time we will come out with success. At that time, I will meet you or we will meet you with success. And as he rightly predicted, the SLV 3 was a grand success, and Dr. Kalam was its project director. And what happened like that, like the earlier time, press people are waiting, and at that time, the press was addressed by Dr. Kalam. So Dr. Kalam also at that time, what he told, it is the success of our team. It is a teamwork which made the project a great success for India. So like that he told. He has not owned the responsibility. He told that it is not myself, it is my team which is responsible for the success. So that is the type of people we had in ISRO. And the other man with white shirt, so he is Dr. Srinivas. He is the man behind the success of our launch vehicle technology, starting from PSLV to the present GSLV, the giant vehicle. So he is the man responsible for the success of the ISRO missions. So we have got the great leaders from Sarabhai to Dr. Narayanan, and with this leadership, recently we also had the success of the GSLV mission. So like that, we have got great leaders who has taken ISRO to the present position and to a greater height. Just I wanted to quote Dr. Narayanan's interview to Hindustan Times recently. So what he told, today we are a vibrant and respected space organization. This has not been done by one man, but by a generation of leaders starting from Sarabhai to Dhawan. So, whatever thing he told, anyway, tomorrow also we will be talking about Dr. Narayanan also. So, we have got leaders like Sarabhai, Dhawan, U.R. Rao, Kasturi Rangan, Dr. Somnath, Sivan, Professor Karan Kumar, like that, we have got great leaders because of them only, and each one has contributed differently for the organization. Now we can see Professor U.R. Rao and the Bangalore Satellite Center is named after him. It is called Professor U.R. Rao Satellite Center, and this is Dr. Kasturi Rangan. They are responsible. Are you able to see the correct slide? Hello?
Yes, sir.
Now, are you able to see? Okay.
Yes, sir, please.
Yes, sir. Yes, sir.
Now I am showing a slide with two satellites and a big satellite. Are you able to see?
ரெண்டு அது நீங்க ஷேர் பண்ணதான் இருக்கும் அவருக்கு ஷேர் பண்ணது இல்லைங்களா?
Can you able to see the slide?
You can see the slide with the satellites.
அப்படி இருக்கட்டு.
Yes, sir.
Okay. Okay, now, so they are responsible. Why I have put the two people, Professor U.R. Rao and Dr. Kasturi Rangan. Yeah, they are responsible for the indigenous development of our satellites. So you can see in the satellite, the small satellite with solar panels. So this is a remote sensing satellite developed by India. This one is would be this particular satellite is bought out satellite from US. And the right hand side, a big satellite with solar panels on two sides. This is a communication satellite built by India, our ISRO, indigenously. So the two persons responsible for building our own satellite is Professor Rao and Professor Rangan. And they have also, as a chairman of ISRO, they were also contributed a lot. It is not only the rocket, it is the satellite is also developed indigenously by ISRO. Now, the journey started from 21st November 1963 from the remote coastal village called Tumba. So, on that day only, the first rocket has flown from Indian soil. So, from then onwards, as rightly told by my earlier speaker, my friend Mr. Jayachandran, from 1963 onwards, we have started our space journey and there is no going back. Then onwards, the India's name is growing high and high. Okay. Now we have, as I told you, we started from Tumba, Thiruvananthapuram. This is development of rockets for both remote sensing and Indian INSAT, that is communication satellites. And we have got a facility at Mahendragiri, and we have got facility at Chandigarh, Dehradun. All over India, our ISRO centers are developed, and each one is having its own function, and they are doing their own assignment of work. For example, if you see Hyderabad, this is National Remote Sensing Agency. They are actually analyzing the remote sensing data, and from that it will be delivered to the needy people. It can be state, it can be a state government or central government, or even private people can approach our Hyderabad center and get data from them. So like that, Sriharikota is our launch pad. Tirupati, we have got a antenna testing thing. And Asan, it is a master control facility for controlling mainly the communication satellite. Bangalore also, we have got a lot of centers like tracking of the satellites, and our deep space mission tracking also is done from the unit at Bangalore. So Ahmedabad is catering to the application type, space application, how you can use the space technology for human need. So that part of the work is done by Ahmedabad. So communication satellite, most of the communication satellite, if you see, you can see the Hindu newspaper, if you see, you can see the India map with the cloud over there. So this part of the thing is done by our Ahmedabad unit. It is called Space Application Center. So like that, actually, our ISRO integrated India. We are starting from the southernmost tip up to the top. We have got facilities in India by ISRO. So it is really truly integrating our country. Okay, now I will just see. From a humble start, this is the first rocket which was launched from Tumba. This is a small rocket. It is 1963, though it is a bought out item. Subsequently, okay. Okay, now are you able to see the rockets? A small rocket and a big rocket.
Yes, sir.
Okay, so this is our 1963 we have started, and from 63 we have grown to this much big. This is GSLV Mark 3, biggest rocket developed by ISRO. And this is the one which is going to be used for taking man to space. Okay, next slide. So like that is about rocket. Now like that, from small satellite, this is Aryabhatta, which is built by India or ISRO indigenously. The mass of the satellite is only 360 kilogram only. And from there, we have developed a bigger satellite. This is a satellite having weight up to 6,000, almost 6 tons capacity satellite. So all these satellites are built at our Bangalore center. It is called URSC, URL Space Center, Satellite Center. Okay, next slide. How is it possible? How we have made the success in space mission? So now let us go into the detail. Quality, as I told, quality is the mantra for success. Total quality is the motto of ISRO. Our motto, if I say simply, test as you fly and fly as you test. So whatever you are going to fly, you should test it fully. And you should fly how you have tested, like that you should fly the thing. So this is being practiced in all areas, both rockets as well as satellite. This particular philosophy is being followed by us. Now, a small video clipping just I want to show. Are you able to see the picture? Okay. Okay, now I will just start the video.
9, 8, 7, 6, 5,
My dear friends, I am extremely happy to declare that PSLV C-51 successfully launched in the precise orbit of Amazonia 1 today. In this mission, India and ISRO feel extremely proud and honored and happy to launch the first satellite designed, integrated, and operated by Brazil. My heartiest congratulations to the Brazilian team for this achievement. The satellite is in very good health and solar panels are deployed and is functioning very nicely. Let me congratulate and compliment the entire Brazilian team. Also, my best wishes for the Brazil engineer for the future operations and the future life of the satellites and utility of satellite for the Brazilian civilian community.
Okay. Now, it is the 2 Ruby note issued immediately after the success of the Aryabhatta. So, this Aryabhatta satellite was developed totally indigenously by ISRO, and it was launched from Soviet in the year 1975. So why I want to tell this is, you have seen in the video clip, we have launched a Brazilian satellite in 2018. It is indigenously built by, first satellite built indigenously by Brazil. You all know where is Brazil. And they have got in their doorstep a launch pad, French Guiana. They have not gone there, but they have come to India. Probably in the video clip you might have seen there is a graph. One is the set track and another one is the path of the rocket. Very precisely, we have put the Brazilian satellite, the first Brazilian satellite, into the right orbit. And that was the success formula of ISRO. So why the Brazilian fellows came to India is only because, not only Brazil, so many European countries, even countries from eastern side also, they are coming to India to launch their satellites. So that is the capability and the ability of Indian space program. And how it is possible? It is by the meticulous quality techniques and quality principles followed by India. Okay. Now, here, this is the infamous 2000 rupee note, which we all know. So, here you can see my earlier speaker, Mr. Jayachandran, told you about Mangalyaan. Actually, here I wanted to add, for the Mangalyaan project, Sri Jayachandran was the project director, and he is responsible for delivering our inertial systems to Mangalyaan. Here you can see there is a small orange color circle is there. 1, 2, 3. Another one is in the back, it is hidden. These 4 things are called reaction wheels. So this is controlling the attitude of the satellite. These things are delivered from Trivandrum. And Sri Jayachandran was the deputy project director for this mission. And already he talked about the Mangalyaan mission. And it was launched actually in 2013. And 2014, we have reached the Mars orbit. He has already told what is the distance of Mars from Earth. It is millions and millions of kilometers from Earth. So that is the reason it took that much time to reach Mars. And what is the life of this satellite? The rated life of the satellite is only 6 months. It is only a half year. It has to work half year circulating Mars. But in the real time, if you see, it has worked almost more than 7 years. This particular satellite has worked in the orbit. How is it possible? It is again by the quality principles and quality techniques followed by our engineers. So that's why I just wanted to put this particular thing. Though the 2000 rupees note is not, but the Mangalyaan served more than that. So this is really a pride for us. Now, just I wanted to tell you about the 9 important dimensions of quality. Next slide. Are you able to see the 9 dimensions of quality?
Yes, sir. Yes, sir. Yes. Good, good.
Yes, okay. Now, the first and foremost thing is performance. For any system, anything, it should perform in its rated function. What for it is rated? What for it is bought? So that is the thing. So the performance is very important. For example, you are going to buy a car. So what is the performance? The performance is it should be comfortable. So we are buying car because we need comfort. So riding comfort should be there, and moreover, it should be fuel efficiency. So these are all the characteristics wherein we talk about the performance. And the next thing is features. What are all the features available in the thing which we are purchasing? So features in the sense. So again, I just wanted to go to the car. The features. So now we have got even Wi-Fi connectivity is there in the cars, and we have got good stereo and airbags. These are all the features which is required. So the quality covers the features also. And conformance. Conformance is, so what is the specification of the car, and it should adhere to the specification. So that is called conformance. The fourth point is reliability. So you know what is reliability. So when I buy something, it should work for at least this many years. If it is more, it is a bonus for us. So the rated life is there for each and every commodity which we are buying. Even suppose you want to buy a eatable, a packet is there, and there will be a seal. You should best before 2 months. You are going to buy from a bakery. You want to buy a cake, so you should use within 4 days. That sort of thing should be there. Now the food and safety is very strict. They see the thing strictly. So this is the thing which is called reliability. That particular thing which we are buying, which we are using, should serve the rated purpose. So it is for this many years. So like that, our satellite also is rated for few from 2 years to 7 or 10 years. It is supposed to work in the orbit. So then only we can say this is reliable. Like that, durability. So this is again almost you can like reliability. The durability is also an important characteristic of the quality. Then service. So this is mainly for ground application. So suppose you are buying a car. If there is poor service, what you will do? You will next time you will go for Any question is there? Okay. So service. So the serviceability should be good. So if good service is there, then only people will go for that. And here also in space technology also, this is applicable. And now we have got technologies so that we can do servicing remotely the spacecraft or whatever thing you can do it. So this is an important dimension of quality. And response, how you are able to respond to your query. So that is more important. If your response is good, then your quality is good. If your response is poor, the quality is poor. If your response is poor, you will not go. You are going to, again, I will go to a normal thing. You are going to a hotel. You are going and sitting, and nobody is bothering you. The next time you will not go there. So this is the thing. So the response, you should be treated properly. So that is more important. Then the eighth point is aesthetics. So how it looks, a car you are buying, the shape of somebody may like the shape with some designs. Somebody may not like at some color, some attractive colors. Recently, I have seen harvest green. So first, what is that green? So green means we will be talking about green. So what is harvest green? So it is a mix of yellow and green. So you all, most of the people are from Kanyakumari district. You know how during harvest time, how the paddy field will look like. So that sort of green. So like that, aesthetic points. So color or shape of the car, like that, you may like. So that also you should satisfy. That is one of the important dimension of the car or whatever may be the thing. Then finally, the reputation. The company should be a reputed company. Like we say Toyota, Honda, or Suzuki. So these companies are reputed companies. So we normally go for buying things from a reputed company. So like that, ISRO is a reputed organization. That is why our government of India is depending. Recently, you might have seen our finance minister has allotted a good amount for ISRO. So if you are not having reputation, you will not get the money. And if you are not having reputation, the foreigners will not come to you for launching their satellite. So the reputation is important. So ISRO is having good reputation. That is why we are liked by both our government and other countries. So these are all the 9 dimensions of quality which is applicable to any product, including space things. Now, the reliability and quality practices. What are all the things important for the success of our Indian mission? Next slide. Reliability and quality assurance practices. The role of quality assurance begins from the design stage itself. Normally, we used to think quality comes at the end. It is not correct. Quality should start from the beginning stage itself. For example, why I have put the design stage? Because we are doing a design. That is why design stage. It is applicable to anything. It is for automobile or a motorcycle or anything which you are making. The design is important. And if it is a service, then service also, what is your plan? That should be clearly spelled. And the role of the QA engineer or quality engineer, quality assurance activity begins from the design stage itself. And the next one is reliability analysis. Reliability analysis is also an important thing which we have to do, especially for space system as well as any moving system. The reliability analysis is the foremost thing we have to do it. And I will come out what are the reliability analysis I will discuss in detail. This also should be initiated in the initial stage itself, and it should be updated as and when the progress is being made. As I told, design stage, that is from the proto stage itself, we have to do the reliability analysis up to the realization of the product. The reliability analysis, it is a continuous process. And testing. Testing plays a major role in achieving the success. As I told, first slide I told, test. As far as our space community is concerned, testing plays a major role in achieving the success because it gives confidence for us to further proceed. So testing, if it is testing and we have got a good result, we will go ahead. If there is a problem, we will again go back. What is the problem? We will discuss. Again, we will realize the product and do the testing. So testing is a major thing. And what are the type of testing which we are doing? I will deal in details. And finally, the meticulous review mechanism is one of the success formula of ISRO. Review. Whatever thing you are doing, it should be reviewed thoroughly. So that is very important. And this ISRO is actually, I can say proudly that we have got an excellent review mechanism. That is the reason we are able to succeed in most of the cases in the first attempt itself. Suppose if you take Mangalyaan, for example, the first mission, no other nation has succeeded in reaching the Martian orbit in the first attempt. And India is proud, I can say proudly that we are the first to reach in the first attempt itself, and we are the fourth nation to reach Mars orbit. So it is possible. How it is possible? It is because of the meticulous reliability and quality assurance practices which we have been following from 1963 onwards. Next slide. And what are the different, I told you about review. What are the different phases of review? So first, concept. So it is, you can say it is in the drafting office, it is in the drawing board, it is in the drawing stage. So at that time itself, the thing will be the product, I mean the drawing or the concept will be reviewed. Subsequent to that, we will come out with a baseline design. That is, my product should be like this. So the baseline design review will be done. Next slide, I will just give one example. Here, I told you about Mangalyaan. We have seen, I have shown you 4 systems. In orange color, I have shown you 4. This is called reaction wheel assembly. The reaction wheel assembly or reaction wheel mechanism is controlling the satellite. Like it is like a steering wheel. This is in the how in the car the steering we are with the steering we are controlling the car. Like that, the satellite is being controlled by the reaction wheels. In most of the satellites, we used to have 4 reaction wheels, and here there are. I was just talking about the concept, then baseline. So here, baseline I can have choices. Here, the things, the circular thing, you can see 1, 2, 3, 4, 5 spokes, 5, 6 spokes are there. So this is a flywheel. This particular flywheel will be rotating continuously in the orbit at a speed of say 3500 rpm or 4000 rpm revolution per minute. And this is also a reaction wheel. This is a disc type of flywheel. So you can see there is no spokes. This is a solid material. To reduce the mass, we have removed some masses uniformly. So these things we will discuss in detail, and we will finalize what is the type of flywheel I have to use for the reaction wheel. Okay. Yeah. Now the conceptual review, baseline design review, preliminary design review. Now the concept is finalized, baseline is finalized, then I will go to the preliminary design review, and after the design review, I will be realizing a product. It is called a proto model or proto flight model or a qualification model. You can say whatever name you want, or it can be an engineering model. So after the preliminary design review, we will be releasing the product, and it will be thoroughly tested. All sort of tests. The testing part I will come. Then the test results will be critically reviewed. And if there is a problem, we may have to correct it, and again you should go back, do the modification, iterate, test it, come again for the critical design review, and once the system is cleared by the critical design review committee, then only it will be flown in the orbit. It is applicable for the rocket as well as satellite also. Though I am telling the satellite, each and every system will be reviewed, will undergo this particular process. In the earlier phases, I remember maybe during the indigenous development of our Indian national satellite, INSAT 2A, at that time, either critical design review or preliminary design review, it will take weeks together. So that much stringent review will be there. Then only now we have matured, and now the number of days also have come down. Then, prior to the launch of the satellite, there will be a pre-shipment review. The satellite, it has to move from Bangalore to Sriharikota. So, before shifting the satellite, again, it will be reviewed by the highest forum. It is called a pre-shipment. Any problem, any thing will be reviewed in detail. Threadbare, it will be, if required, the satellite will be called back, and we will be doing some additional testing and other things. So it will be reviewed, none other than the chairman of ISRO will be there, and there will be a high level committee. They will review the results. And here also, the role of QA engineer is very important. The final say will be by the QA engineer. The QA engineer says that there is a problem. This particular issue is not closed. Then they will see that that particular problem is non-conformance or whatever word you use, that will be cleared, then only it will be shipped to the Sriharikota for launch. There also, again, the further testing will be there separately, and there will be a mission readiness, whether we can launch the satellite, whether we can do the launch. So, mission readiness review will be there. Then only the rocket will be launched from our spaceport. Then, even after that, it doesn't stop. Post-flight analysis review also will be there. If it is success, why the success, how we have got the success, that also will be reviewed. If there is some error or any deviation, that also will be done by the post-flight analysis review. So these are all the different phases of review mechanism in our each product or each system developed by ISRO will undergo. Next slide. Okay, now this about the different design options I have already told. Okay, next slide. Next is reliability analysis. Reliability analysis, as I already told, so this is having different phases. The first one is failure mode effects and criticality analysis. This particular operation or this particular analysis we do for every system developed by ISRO. For example, I will one small example I will tell you. you are having a, because we are the 1960s we have born. So at that time, we use fountain pen. So the pen, if it is not writing, what will be the reason? So it can be so many things will be there. So this particular failure mode effects and criticality analysis, it is a bottom to top approach. Suppose the particular thing, the one small part. Example, you take a car. Particular small thing is not there, then the car may not start. So there may be a problem. There may be a short circuit. So like that, each and every product, every part, even a minor part, will be discussed, will be reviewed. Their failure, if it fails, what will happen? Earlier, I talked about there is a reaction wheel which is controlling the satellite. The reaction wheel comprises of an electrical motor, a flywheel which is rotating, and there is a bearing unit. Then this particular fellow will be covered because we have to test this particular system at an RPM of maximum 5,000 RPM. We have to rotate this, and this particular system will be in a closed environment. Okay, just I will show you the previous thing. Yeah, so here this is the electronics part. Okay. Now, are you seeing the figure, the two figures which I have shown you earlier? Are you hearing?
We can see the figure.
Two figures are you seeing?
No, sir, it is visible.
It is visible. Okay. So this is a reaction wheel thing. You can see this is the flywheel part, and this is the electronics part. This is the cover. The thing, entire thing will be closed using this cover, and below this thing we have got a bearing unit. And okay, here also you can see the electronics and the flywheel. This particular flywheel will be rotating at a speed of 5,000 RPM, or from 3,000 to 5,000 RPM. This will be rotating. Suppose if you take a bearing unit, so bearing, we need for rotating a bearing, we need lubrication. So the lubrication, if the lubrication is not available, the bearing will fail. So how the lubricant non-availability will happen? Suppose this particular, we are sealing this particular reaction wheel. If it is, there is a leakage, you all know that space environment will be high, very high vacuum. So what will happen is, if there is a leak, the whatever lubricant available in the bearing unit, bearing, will be drained out from the bearing, and it will go through the hole in the thing. So there should not be any leakage. And for the failure of this bearing unit, loss of lubricant is one of the things. If the lubricant is lost, the bearing will fail. If the bearing fails, what will happen? There will be high friction will be there, and finally the entire unit will be jammed and it will not rotate. If it is not rotating, what will happen? We will not be able to steer the satellite. If the satellite is not steered, it will lose its attitude. If the attitude is lost, we will not be able to control the satellite. It will be drifting. It will go to a different orbit, which is not a favorable thing. So, a small failure of the lubricant, how it affects the satellite. So that is the thing which I want to say. So in the failure mode, effects and critical analysis.
தம்பி சீக்கிரம் போ இங்கிலீஷ் முடிச்சிட்டியா
Okay, now you are seeing the reliability analysis slide. So earlier I have told you about failure mode, effects and criticality analysis. Why I have told the bearing example in a reaction wheel? Because it is a loss of lubricant. So it is inside. It is a lubricant is a liquid. It is the quantity is about 50 milligram only in a bearing. 50 milligram of lubricant. If it is lost, what is happening? The entire satellite will be out. So the failure starts from the minor part, small part. I will not say minor. It is a critical part only. The small critical part, say it is a bearing, can be bearing, it can be a lubricant. It fails. If we lose the lubricant, find it causing a major effect on the entire satellite itself can be lost. Like that, each and every system which we are using in our spacecraft we will be doing the failure mode effects and the criticality analysis. Then we find that this particular thing is weak, then we will be doing what is the corrective action. So lubricant loss means there should not be any leakage and there should not be any small quantity of lubricant we should not use. Like that, so many things. Then the satellite is supposed to work for, as I told, from 3 to 5 years to 7 to 12 years it has to work. For example, communication satellites, we have got the life of the satellite from 10 to 15 years it has to work. And 10 to 15 years, whether the 50 milligram of lubricant, whether it will serve the purpose. No. Because as and when the particular thing is rotating at a high speed, there will be some loss. The loss will be inside. Small quantity will be lost. It will be like in vapor form, it will go out from the bearing. So what we have to do? We have to again refill. Anyway, I cannot go there and do a refilling thing. Or I cannot do like a car. So car, if it is breakdown, we can go to the workshop and do a breakdown maintenance. Here I cannot use. So what I should use? So there should be a additional lubrication I should send. So what for that only we have got some method, like some reservoir should be there, and that reservoir should feed. That reservoir will contain lubricant. Whenever I need lubricant to the bearing, that reservoir should supply. So for that, different things are available. Like we have got static reservoir, dynamic reservoir, so on. Like that, so many things are there. So that part I am not going into detail. So that is, suppose there is a problem, how the corrective action is being taken. So this sort of things will be carried out during the failure mode effects and the critical analysis time. So this will be done from the conceptual design stage itself. This will be done, and during realization phase also this will be done. If there is any requirement, we will be updating it. So these failure mode effects and criticality analysis is very important for a space-bound system. And for your information, this particular FME, the criticality will be there, FMEA will be there. for each and every automobile which we are using, this particular reliability analysis is being done. Any automobile manufacturer, if you see, they will be doing FMEA, that is failure mode effects analysis they will be doing. And here, additionally, we are doing the criticality analysis for aerospace things. So this is one of the important reliability analysis which we are following for our rockets as well as satellites. Then derating analysis. Derating analysis is the one which gives confidence and for the system. So this is mainly applicable for electronics and electrical things. So here, what is the maximum capability of a particular, say it is a diode, it can be a transistor, or it can be IC. So that thing is estimated by doing a derating analysis. This is also one of the, before integrating any component, this derating analysis will be carried out. This can be done as a component level, and this will be done as a system level also. This derating analysis will be done. The third one is fault tree analysis. Actually, this is a reverse of FMECA, failure mode effect and criticality analysis. In fault tree analysis, it is a top-down approach. This one is bottom-up approach. This is top-down approach, fault tree analysis. So a failure has happened. Then from the failure, then from top we will come down. How it can happen? How it can happen? So like that, this fault tree analysis is also one of the important reliability analysis technique we are doing. The fourth one is risk analysis. Risk analysis very important. Wherever human rated things are there. For example, our Gaganyaan mission risk is important because the safety is here, quality, reliability, and safety is also coming into picture. If you see the recent ISO standards, the risk is the one of the major factor which is being considered. So this risk analysis is to be done. So wherever risk analysis we are doing, based on the risk, we have to do a corrective action. So this is very important reliability analysis technique which we are doing. Then finally, the reliability prediction. What is the confidence you are having on the system? So this is done by the meticulous testing of the system. For example, for electronics product, already we have got a ready-made data is available because already millions of components are tested and the reliability is being established. Whereas for mechanical system or mechanisms, we have to do the reliability prediction by doing testing. So reliability prediction can be carried out for both mechanical system as well as electronic system. Okay, next slide. So this reliability analysis is a very important thing which the QA people should do. I told you about the testing. So testing is a very important thing in our ISRO community. So one is functional testing. So functional testing, by functional testing, what I mean is, it is starting from simple electrical test, then each one is rated for a function. There will be a specification. The specification should be validated by the functional testing. As I told, the reaction will told. The reaction will, we monitor the current, we estimate the torque, and we estimate the friction. All those things will be done during the functional testing. And each one will have a peculiar characteristics. And based on the characteristics, we have to do it is a bench test. It will be done in the bench. There is no environment. It is simply it is called a bench test, we can say. So functional testing is a first and foremost test any system has to undergo. The next one is environmental testing. Why we have to do environmental testing? Here I will just talk about the spacecraft. The spacecraft undergoes thermal environment, humidity environment, vibration, shock, EMI, EMC, and thermovac. So thermal, one small example I told. Aryabhatta we have launched from Soviet Union. Soviet Union, you know the climate. So there, even sub-zero temperature it can go. So I am going to launch the satellite at that condition. So my satellite should work in that condition also. So I have to do a thermal testing. So for that, we have got dedicated thermal chambers. There we have to, because we know what are all the thermal condition this particular system will undergo. So that thermal condition will be simulated using a thermal chamber, and the system will undergo a thermal testing. So likewise, humidity. So some places humidity will be high. So the satellite will be exposed to the humid condition. So the humidity level also it has to undergo. So at that time only, there will be problems like some electrical problems will be there. All those things will come out while doing this thermal testing, humidity testing, etc. Then comes the vibration testing. During launch time, there will be big vibration. The vibration will be felt by the satellite also. During that vibration time, the satellite has to survive. So whether the satellite, not only satellite means the parts inside the satellite should survive. For that, before integrating a satellite, we will be doing the vibration testing. So this vibration, what are the levels we will be knowing, because by doing testing, simulation, because now we have got lot of software techniques, so we will be knowing what are all the vibration levels this will undergo during the launch. So this test will be carried out, vibration testing. And like that shock also, this is also the satellite will be experiencing the shock. Excuse me. So the satellite parts individually it will undergo vibration test. The satellite itself as a whole will undergo whatever test I told, thermal, humidity, vibration. Then EMI, EMC test also will be carried out. Then finally thermovac. After all, thermovac means both thermal as well as vacuum testing. Why we have to do a thermal vacuum testing? Because I am going to put my satellite in space. The space environment we all know. So the thermal environment will be there. Not only thermal, vacuum environment also will be there. So I know that in the particular orbit, what will be the thermal condition, vacuum condition prevailing in that particular orbit. So that thermal and vacuum environment, I have to simulate for the components or for the products which are being integrated in the satellite also will be tested. And the entire satellite will also undergo thermovac testing. The thermovac test, it will undergo maybe starting from 10 to 15, even months together it will take. So that sort of stringent testing will be done. Then the satellite will be taken out, and again we will be doing functional testing. Whether the functional testing which I have done initially is matching. If there is a deviation, again we have to do what is the deviation. We have to do a corrective action, and we have to repeat all the tests. So that's why I told test as you fly and fly as you test. So the testing plays a major role in ISRO. Here you can, next slide, you can see a satellite. So you can, so this is the satellite, this is the solar panel. The solar panel is now, it is open, it is in open condition. This is one side. Another side, this solar panel is not opened, it is not deployed. It is stowed condition. It is in folded condition, you can say. So to do that in ground itself, because while launching, this panel will be folded. In that condition only it will be launched. Once it is launched, this panel is to be deployed. So how to, it will be tied using a wire rope, and in the orbit, this particular wire rope is to be cut. So that is done. It is wire rope, we can say it is called a cable. The cable is to be cut. Once the cable is cut, this panel will be like ஒரு பாய் எப்படி விரியுதோ அதே போல இந்த சோலார் பேனல் ஓப்பன் ஆகும் space environment. So like that, the panel will be deployed in the space. Why I told this particular thing is, this cable cutter is delivered by a unit from VSSC, Trivandrum, and it has never failed. You imagine this cable cutter, like FMEC, just you now you can recollect. If this cable cutter fails, what will happen? We will not be able to deploy the solar panel. So if solar panel is not deployed, there will not be no power. The satellite will not get any power, and the life of the satellite is out. So it is, though it is a small thing, cable cutter, it may be hardly less than a kg weight, but it plays a very crucial role in satellite. The cable cutter, why I have quoted is, in ISRO's satellite missions, we have not faced any failure because of cable cutter. Whereas cable cutter will be this side, and whereas one of our, in the earlier days I told, we used to buy satellite from foreign countries, and it will be launched by foreign rockets. The satellite failed because of the non-deployment of the solar panel. At that time, because it is a bought out item, the cable cutter is also bought out. It is built by a foreigner or foreign agency. It has not worked. So we lost the satellite. One of the INSAT-1 mission, INSAT-1 series, all the INSAT-1 series we have bought from other countries, launched using the launch vehicle of other countries. So this is, there is no failure of cable cutters in the entire launch history of Indian space program. So I am proud to say that. So this is our biggest achievement. Why I have told the cable cutter is, I have done my first failure mode effect and criticality analysis for this particular cable cutter. That's why I have quoted this as the example. Okay, next slide. This is on the thermovac chamber, space simulation facility. Space simulation, space means thermal as well as vacuum condition. You can see people are standing inside a thermovacuum chamber. So inside this, we put our satellite and do the testing. So like that, in ISRO also, in ISRO inertial system unit also, we have got thermovacuum chambers where we test our products like reaction wheel assembly, cable cutter I told, cable cutters, then like that, whatever our Jayachandran told, inertial reference unit, so many things. All those systems will be tested in this type of thermal. It will be a continuous test, it will be 24 hours continuously 24. You cannot stop the test. It will be tested in continuous mode. And during that, the entire performance of the satellite will be monitored. We will not simply put it in the thermovacuum chamber. It will be tested also in that condition. And any deviation, anything is there, it will be immediately reviewed and corrective action will be carried out. So testing plays a very major role in the ISRO's products. Now I will just talk about the review mechanisms, which configuration control review. Suppose if I made a drawing, this drawing will be configuration controlled. I want to change anything, then it has to undergo the configuration control review. Once they review it, then only this will be approved. Configuration control board should review and accept the product. The next one is non-conformance control review board. Non-conformance, what is non-conformance? There is, if there is a deviation. I have got a specification. If the specification is changing, if it is deviating from the specification, it is called non-conformance. So the non-conformances we cannot leave as such. That non-conformance, and the designer cannot take a decision. He knows because it is his baby. He will say that okay, there is no problem. But this needs to be reviewed by a non-conformance control review board. Has to review the non-conformance or deviations. Then only we can clear the product. So once this non-conformance control board clears, then only this particular non-conformance can be, suppose I am making a mechanical hardware, say a screw or washer. If the washer is out of spec, there is a small millimeter change. So this particular thing needs to undergo this particular review board, and once they clear it, or they may do some corrective action, or they may do some testing. You do the testing. If it is okay, then you can use it. So the recommendation of the non-conformance control review is to be fully done by the product evaluation agency. Then the failure analysis board. Failure can happen at any time. I told you about testing. Vibration testing I am doing. During vibration testing, I found that there is a component failure. I cannot simply change the component and go ahead. No, why the component has failed? So high vibration level has gone to the particular component, or it is a faulty component. All those things we have to totally review in the failure analysis board. Then only we can go ahead with the further integration of the product in the system. Like that, satellite also it is applicable. If there is a failure, then it will be a big review, failure analysis, why it has failed, how it can fail. All those things will be thoroughly reviewed by a very knowledgeable person. Even sometimes the people from academia and R&D institution also, expertise in R&D institution also. We take their advice and do the failure analysis, and the recommendation will be implemented. Then system review board. This is also a major thing. So the entire system will be reviewed by this particular board. So that the whole system, it is okay or not okay, that will be told by the system review board. So these are all the review mechanism. Every system of ISRO has to undergo. Okay. Now we have seen the importance of quality. As I first told, the quality will be felt only if it is absence. So thank you very much. And the quality is never an accident. It is always the result of intelligent effort. The intelligent effort is nothing but whatever reliability analysis, testing, review mechanism, whatever thing I told, that intelligent effort the product should undergo, then only you will get quality. So again, I will say quality is never an accident. It is the intelligent effort. Thank you very much for your listening.
Thank you, sir, for the excellent talk on quality ruling space. We have understood the importance of quality assurance practices followed in ISRO for the successful launches. We have learned the requirement of various review mechanisms being followed in ISRO for improving the reliability of the space products. Thank you for stressing upon the reliability analysis being carried out in ISRO for all the missions. We have also understood the levels of testing each launch vehicle and satellite is undergoing before launch. Thank you for explaining in detail about the reliability analysis like failure mode effects and criticality analysis, derating analysis, risk analysis, and reliability prediction. Sir, your knowledge, insights, and passion have genuinely motivated and educated us. We appreciate the time and effort you put into preparing for this session and the clarity with which you presented such complex ideas. You have shared with us not only knowledge but a glimpse into the vast and infinite landscapes of thought. On behalf of Marthandam College of Engineering and Technology and all our participants, we thank you once again for your generous contribution to making this session on an enriching experience. Thank you all for joining today's session. While we are wrapping up here, there are more sessions with different speakers coming up. I hope you enjoy them and I am looking forward to see you again in the upcoming session. Thank you.
Thank you, madam, for your kind words. Any questions you can ask? Hope everyone understood. That's why there is no question. Okay, thank you very much.